Have you ever wondered if we're truly alone in the universe, or if there's far more to reality than what we can perceive? What if the James Webb Space Telescope eventually proves that we're living inside a black hole? Join us as we explore a mind-bending theory that could upend everything we thought we knew about the cosmos. So, what exactly is a black hole? They sound like something out of science fiction horror film, and in many ways, the truth is even more terrifying. Far from being just dark voids in space, black holes are immense amount of matter compressed into an unimaginably small area. Picture a star 10 times the mass of our sun crammed into a sphere no bigger than New York City. The resulting gravity is so intense that nothing, not even light, can escape its pull. Scientists have been fascinated by black holes for centuries, ever since the idea emerged that an object could become so dense it would trap even light itself. Our most well-known understanding of black holes comes from Einstein's theory of general relativity. In simple terms, when a massive star dies, it leaves behind a dense core. If this remnant is more than 3 times the sun's mass, gravity overwhelms everything else, resulting in a black hole. But spotting a black hole isn't easy. Because they emit no light, researchers rely on indirect evidence, like how black holes affect nearby matter. For example, as a black hole passes through a cloud of gas or dust, it pulls that material in, creating a glowing disk of heated matter known as an accretion disk. Similarly, if a star strays too close, it may be torn apart, releasing powerful X-rays in the process. Black holes don't just consume, they reshape their environments. They can swallow nearby stars, unleash intense gamma-ray bursts, and even influence star formation, sometimes helping along, other times suppressing it entirely. But where do black holes come from? Imagine a once brilliant star meeting a spectacular end in a supernova explosion. From the ashes of that cosmic death, a black hole is born. Most form from stars far more massive than our sun. Stars with slightly less mass become neutron stars, astonishingly dense, but not dense enough to trap light. When a star crosses that critical mass threshold, however, it collapses under its own gravity, and strange things begin to happen. Near the surface of a collapsing star, time itself behaves differently. To a distant observer, time appears to slow near the event horizon, the point beyond which nothing can return. It's as if time ticks slower and slower the closer you get to the edge. And sometimes black holes collide. When 2 smaller black holes merge, they create a new, even more powerful gravitational beast. If a neutron star crashes into a black hole, the result is a cosmic monster beyond comprehension. For decades, scientists have been trying to grasp the true scale of these enigmatic objects. Black holes generally fall into 2 categories, stellar mass and supermassive. But even small is relative. Stellar mass black holes, born from dying stars, can range from 10 to 24 times the mass of the sun. There could be anywhere from 10 million to a billion of them in the Milky Way alone. That's an astonishing number of invisible engines roaming our galaxy. Then there are the giants, supermassive black holes, millions to billions of times more massive than the sun. They sit at the heart of nearly every large galaxy, including our own Milky Way. These behemoths act like cosmic anchors, shaping the structure and fate of entire galaxies. The late physicist Stephen Hawking spent his life unraveling the mysteries of black holes. Though many of his theories couldn't be tested during his lifetime, the tools to explore them may finally be in our hands. One revolutionary instrument is changing everything, and we may not be prepared for what it's about to reveal. The James Webb Space Telescope, better known as the JWST, isn't just another space telescope. It's a groundbreaking scientific achievement, a symbol of what human ambition and ingenuity can truly accomplish. While past telescopes like Hubble have served us well, JWST is in an entirely different league. To put it in perspective, Hubble now seems like a small stepping stone in comparison to this colossal leap forward, costing an eye-watering $10 billion. Yes, with enough zeros to make your head spin, JWST was made possible through a monumental collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, along with contributions from over 300 universities and institutions worldwide. Of course, such an ambitious project doesn't come without its risks. JWST's mission is not for the faint of heart. It's journeying into the unknown, boldly pushing the limits of our understanding of the universe. After a successful launch, NASA confirmed that the telescope has enough fuel to operate for more than twice its minimum mission lifespan of 10 years. Traveling over 1 million miles from Earth, the telescope reached its permanent orbit around the Sun. During this journey, it successfully deployed its enormous 5-layer sun shield and unfolded its primary mirror. No small feat, considering both had to be compacted tightly to fit within the launch vehicle. Now, after extensive calibration, the JWST is almost fully operational. One of the most exciting moments came when NASA revealed that the telescope had captured its very first starlight images. The first target was a star named HD 84406, producing a stunning mosaic of 18 scattered points of light, each one captured by a segment of its segmented mirror. Later, a refined image showed those 18 points arranged in a precise hexagonal pattern, marking a major milestone in aligning the telescope's optics. Once fully aligned, the 18 separate images will merge into one crisp, unified picture. With its cutting-edge instruments, JWST is poised to peer further into the universe than ever before, offering insights into the first moments following the Big Bang. It will explore the era of reionization, the cosmic dawn when the first stars lit up the universe and began transforming the intergalactic medium. But JWST isn't just looking back in time. It's also helping scientists in the ongoing search for exoplanets, distant worlds orbiting other stars. Thanks to its advanced infrared sensors, JWST can analyze the light filtering through exoplanet atmospheres, revealing key details about their chemical makeup and possible habitability. Beyond planets, the telescope will revolutionize our understanding of galaxies, how they form, evolve, and cluster together to shape the large-scale structure of the universe. From the earliest galaxies to the majestic spirals we see today, JWST will trace their evolution across billions of years. And perhaps most intriguingly, the JWST is here to help us confront humanity's biggest questions. Are we truly alone in the cosmos? Could we be living in a black hole? It's already making waves with discoveries like the detection of polycyclic aromatic hydrocarbons, PAHs, around supermassive black holes in 3 active galaxies. These ring-like carbon molecules are found everywhere, from the most distant galaxies to comets in our own solar system. Not only are they potential building blocks of life, but their presence also provides clues about star formation and the environment surrounding black holes. The James Webb Space Telescope isn't just a machine. It's a window into our origins, our place in the universe, and the possibilities that lie beyond. Astronomers use PAHs, polycyclic aromatic hydrocarbons, to trace star formation. When ultraviolet radiation hits these molecules, they emit infrared light, which can be detected by the James Webb Space Telescope's JWST mid-infrared instrument MIRI. This glowing signal often points to the presence of hot, young stars. In a fascinating turn, astrophysicist Ismail Garcia-Benit from Oxford University studied 3 active galaxies, NGC 6552 and GC 731, and the renowned Stephan's Quintet, located millions of light years away. His research revealed a striking concentration of PAHs in the central regions dominated by supermassive black holes. But what he found next was unsettling. Intense radiation from these black holes was altering the PAHs, transforming them into larger, electrically neutral versions and effectively erasing the smaller, charged PAHs commonly linked to star formation. The image is almost poetic, molecules vanishing into darkness, with only the larger PAHs surviving by hiding within thin, dense gas clouds, like cloaks shielding them from the black hole's destructive power. This unexpected transformation complicates the work of astronomers, who depend on charged PAHs to identify stellar nurseries. If these molecules are being wiped out near black hole cores, tracing the birth of stars becomes far more difficult. Still, Garcia-Benit and his team are undeterred. They aim to expand their study to more active galaxies, hoping to better understand how PAHs manage to survive in such extreme environments. Their goal is to uncover the unique traits of PAHs in galaxies dominated by black holes, research that could reshape our understanding of star formation and galactic evolution. Adding to the excitement, the JWST may have made one of its most profound discoveries yet: the identification of the oldest known black hole in the universe, estimated to weigh a staggering 10 million times more than our Sun. This ancient giant was detected through faint glimmers of light dating back to just 570 million years after Big Bang. Scientists suspect even older black holes could be lurking deeper in space. This revelation has stirred the scientific community, raising questions about how such massive black holes formed and grew so rapidly during the universe's infancy, when the cosmos was only about 1 billion years old. While this discovery is still awaiting peer review, lead author Rebecca Larson from the University of Texas at Austin is confident that many more ancient black holes remain undiscovered. She highlights how the JWST is revolutionizing our ability to explore cosmic history, unlocking secrets once thought forever out of reach. As the JWST continues its mission, it's uncovering staggering insights and reshaping our cosmic perspective. Its ability to peer into the universe's earliest epochs is allowing scientists to study the first galaxies, which played a key role in reionizing the universe and forming cosmic structures. By analyzing these primordial galaxies, researchers are learning how the first stars ignited and how the cosmos transitioned from darkness into light. Beyond galaxies, JWST is also pushing the boundaries of exoplanet research. Its cutting-edge instruments can examine the atmospheres of distant planets by measuring the light that passes through them. This allows astronomers to detect biomarkers, such as water vapor, carbon dioxide, and complex organic compounds, that could hint at the potential for life beyond Earth. Moreover, JWST is refining our models of how galaxies form, evolve, and interact. Its observations are shedding light on the role of dark matter and the processes that drive galactic growth. With every new discovery, the telescope is bringing us closer to answering some of the universe's most profound questions. In short, the JWST is not just a telescope. It's a time machine, a planetary lab, and a cosmic detective. Its journey through the deep universe continues to astonish, offering glimpses into the very fabric of space and time, and revealing a universe far more dynamic and mysterious than we ever imagined.